So this time we're going to look at finding the average value, and this is something you learned back in Calculus 1. So it's essentially finding the integral of the function between a and b, and then we'll basically divide by b minus a, which is the total distance of the interval. You know, that's basically how finding the average. You know, divide the number of elements essentially by the total number of elements, you know? All right. So what about the average value of a function? Well, ultimately, what's that? So let's refresh a little bit on that. So suppose, to find the average, we're given a function f of x, and yes, from a to b, as usual. And essentially, so suppose this area right here is, I don't know, maybe peanut butter or Nutella, you know, something, or any jam. So, and suppose you grab a knife and, you know, try to get that curvy shape and try to make it into a horizontal line. So the idea of the average value, whatever value you obtain, which is, let's call it c, whatever that value. So this is going to be that value of c will be some value, some constant, which is going to be a horizontal line. But the thing here is that the average value, from a to b, essentially is finding the location, the y location, for which the area of the curve is exactly the area under the rectangle. So that's the average value. So this horizontal line right here, the average value. So that's what the average value is. And of course, we can extend this idea to functions of two variables. Well, again, so we need to recall what do we do with an integral in two variables. Well, for one variable, for f of x. So we are integrating over an interval, over some distance described between a and b. Now, in this case, when we extend this idea to functions of two variables, we are, in order to find the area, or rather the average value, it's the double integral, but in this case we divide by the area because that's what we have in two dimensions. You know, we're describing an area. And so let's do one example. So let's find the average value for f of x equals to xy over the region R, where R is a rectangle in the xy plane with vertices at 0, 0, 5, 0, 5, 3, and 0, 3. All right, so let's sketch the region first before getting into. All right. So number one, let's draw the graph. So that's the point. 0, 0, 5, 0, 0, 3, and 5, 3. So let's draw that rectangle. And find the area, because in this case we're not going to find the difference between the values b minus a, just the same way in the way we did it with the average value for functions of one variable. So in this case, since we're not integrating over a segment, over an interval, this time we're integrating over a rectangular region in this case. So we need to find the area which in this case is 5 units by 3 units, the area is 5 times 3, that's 15. So let's find, in this case, Z average. And Z average is 1 over the area of R times the double integral of R, over R of the function to xy dA. Okay? So, well, let's define this double integral over this region. So in this case, again, we need to determine whether this, whether the region is horizontally simple or vertically simple. And in this case, it happens that it is both horizontally simple and vertically simple. So typically we define it as vertically simple. So we do the y's first, and then the x's. So I'm going to integrate. Okay, so 1 over the area, that's 1 over 15. Integral to xy, and dA will be dy dx. So recall that the innermost integrals, it's an integral with respect to y, so we're going to look at the limits of in terms of y. So in this case, the limit is going to be 0 to 3. And then the limit for the outermost integral, it's going to be, well, the limit in the direction of x, which in this case is from 0 to 5. So let's go ahead and integrate this function. Recall, we're going to do one integral at a time. So the integral up to xy, that's 1 over 15. The integral from 0 to 5. And the integral up to xy with respect to y, that's xy squared. And that evaluated from 0 to 3. And don't forget the dx for the second iteration of the integration. So integrating this, recall that since we integrated with respect to y, we only plug in these limits wherever we see the letter y, not wherever we see x's. So this is 1 over 15, integral from 0 to 5. So that's going to be x times 3 squared minus, well, what happens if we plug in 0? Is it not going to go to 0? So big 0 is fine. And dx. So let's see, 3 squared, that's 9. That's going to give us a 9x. So that's 1 over 15. 1 over 15, integral from 0 to 5 of the quantity 9x dx. And well, the integral of 9x, that's going to be, well, I'm going to take the 9 outside of the integral. And we're going to integrate just x, which in this case it's going to be 9 over 15 times x squared over 2 from 0 to 5, which is really, the denominator will reduce to a 30. So that's a 9 over 30, x squared from 0 to 5. And let's just simplify using calculator. So that's a 9 over 30, and that's a 5 squared minus 0 squared. And simplifying this should give us a 15 halves. All right? Yes?
And the original equation above the example, should it be a y or is that?
Which one?
And the printed equation.
This one, 2xy?
No,
Oh, actually, this should have been a z, actually. A z average. A z with a subscript. Yes, I'm going to fix that PDF. Thank you. Well, what would it mean in this case to find the average value? So, well, we have a surface, you know, and these surfaces could be like spheres, like looking like hills, you know. So this means that this is the value z average equals to 15 halves. So in 3 dimensions, this we would have this this region that we have in 2D here. So from 0 to 5 and from 0 to 3. So essentially, This is the projection of our region into dimensions if we wanted to see in 3 dimensions. Are you guys following me here? Well, so this value right here of z equals to 15 halves, that's actually the height of this box in 3D. All right, this will form a box in 3 dimensions, and that box will have exactly the same volume as the one that we calculated over here on the integral. So that is the volume of this, here looking solid. If we smash it and we suppose it's clay and we give it the form of a box, well, in order to have the same volume, both like the hill looking shape or solid and the rectangular box, they will be the same, in the same way that we did the peanut butter example with the function and the rectangle, right? So that's the average value in 2 dimensions. Well, actually in 3 dimensions technically. So let's do an application to find population density. You know how sometimes when we're reading statistics about population here and that, typically they're telling us some kind of an average population size from communities, So we have this population density function on an island given by f of x equals 5,000 x e to the y over 1 plus 2x squared. So, where x and y are measured in miles and the grid is laid over the island in order to determine this population density at different locations, alright? Well, so they're asking us to find the total population inside of a rectangular area defined by those vertices here. So suppose, so let's make a picture here and let's draw the island first. All right, and suppose we impose a rectangular system here. All right, so we want to know the area or the population in the area defined by the point 0, 0, 4, 0, 0, 2, and 4, 2. So we're going to have this rectangle. We will find the average population inside or inside of this rectangular region. All right. So let's see. So number one, this is what we're going to do. We're going to find the population, the total population, and then we're going to divide by the area of that rectangle to get the actual average of the population. All right. So number one, let's do one at a time. Let's find the total population by evaluating the double integral over the region R of 5,000 x e to the y divided by 1 plus 2x squared dx. Well, not dx, it's actually dA first of all. Alright, so in this case we're going to decide which direction are we going to take. And again, if we look at this region, well, it's a rectangle, so there's no way to go wrong with either vertically simple, defining it as a vertically simple region or a horizontally simple region. But typically we go the order dy dx. Alright, so we're going to treat this as a vertically simple region. So that's going to be the double integral of 5,000 x e to the y over 1 plus 2x squared dy and dx. So recall that the innermost integral, it's an integral with respect to y, so we are going to put limits in the y direction, which in this case is going to go, isn't that going to go from 0 to 2? And for the outermost integral, that'll be an integral with respect to x. So we will need to look at the limits in the direction of x. So in this case, it's going to go from 0 to 4. All right. So let's integrate this one.
Yes.
Yes.
What about 1 over the area of the region?
Oh, we're going to do that at the end. So first we're going to find the total population, and then we will whatever we get, so we don't get too many coefficients and symbols, because look at how big this function is. So in the end we will find the average. All right? So let's evaluate this. Well, in this case we're just integrating with respect to y. Well, the integral of e to the y with respect to y is just e to the y, right? So that's from integral from 0 to 4 5,000 x e to the y divided by 1 plus 2x squared. And that evaluated from 0 to 2. But again, we are integrating with respect to y. We should evaluate this only in the y function that we just integrated, not everywhere else, all right? And that with respect to x. So I will continue highlighting these limits in the variable we're supposed to plug in, just to remind ourselves that we're just evaluating one variable at a time. All right. So that'll be the integral from 0 to 4 of 5,000 x over 1 plus 2x squared. And well, e to the second, that's e squared minus e to the 0, and well, that dx. Well, e to the second power, let's just leave it as e to the second power for now. In the end, we're going to approximate this result to some decimals, but at least e to the 0 is 1. However, in the meantime, I would like to take out these constants, in particular this 5,000, which is a constant. I'm going to take it outside of the integral, along with the result of simplifying this e squared minus e to the 0. That's 5,000 e squared minus 1 integral from 0 to 4 x over 1 plus 2x squared dx. And the reason for this, well, technically that's the best way to go about integration, get the constants outside of the integral, but also to have a clearer view of the integrand right here in order to determine which method of integration would be the best to go about. Any ideas on this one? Just substitution is going to be fine, because, well, it's a second degree. We have 1 degree less, so let's see. So u equals to 1 plus 2x squared, du equals 4x dx, and x dx equals 1/4 du. All right, and if we change the limits to the world of u of 0 and u of 4, we should obtain, well, 1 plus 2 times 0 squared, 1 plus 2 times 4 squared. All right. Changing this limit, well, the first limit will become, the 0 becomes a 1, and what do we have here? 4 squared, which is 16. 16 times 2, that's 32. Plus 1, isn't that a 33? All right, so let's simplify, or actually let's rewrite the integral in terms of u, along with the new limits. I'm going to continue here, so I don't think I have enough space. So that's 5,000 e squared minus 1. That's the integral from 1 to 33 of, what's this? So it's going to be 1/4 du over u. Okay, so let's do some simplification. So number one, let's take this 1/4 outside of the integral, which actually reduces to 1250. And we may go about the integration. And what's the integral of du over u? What's that? ln. All right, ln of u. And, well, technically we should, well, I'm going to put the absolute value bars anyway. Because ultimately the context is about number of people, so there's no such thing as negative number of people. So when it comes to context, you can make some exceptions with the notation. But in the meantime, since I still have a function of view, well, I'm going to leave it like this. So to avoid the back substitution, that's why we did the changing of the limits. This way we can just go about, well, 1250 e squared minus 1 ln of 33 minus ln of 1, which reducing, that's going to give us 1250 e squared minus 1 times ln of 33. So that's how many people live in the island. Well, but I need a number, a number that is easier to read to give me a better idea. So when we read a magazine or something in the newspaper of statistics, well, we don't read these numbers. So let's simplify this to, I have 27,924 people, rounding to the nearest integer. So that's how many people live in the island. So let's see the average in this rectangular region. So that's part B of the problem. All right. All right. So what's the average population? Well, so the average, yes.
Do you have another copy?
So what's the average population density for the region defined above? All right, so all we have to do is find the average, rather the z average, which is 1 over the area times the value of the double integral over the region R of f of x y dA. But we know both values right here. So 1 over the area in this case is 8, because, well, what do we have here? So this is 4 units by 2 units. 4 times 2, yes.
How come you didn't do the 1 over 8 in front?
At the beginning?
Yeah.
Because the first part of the question is the total population. And then the second part is to find the average, which is using the value of the integral, which we got in part A, 27,924. And then we divide by the area to get the average. All right. So this time we did it in 2 parts. So because of how complicated this function looks like, so that's going to be reducing to 3,490.5, and in this case the units would be people per mile squared, because we are finding an average over some area, right? And the area in this case is it's given in miles. All right. So let's see.